Welcome, listeners, to another deep dive. Today we're tackling, well, something fundamental: energy.
That's right. Specifically, kinetic and potential energy, how things get moving and how they hold energy even when still.
Yeah, it's all around us, from, I don't know, a kicked football to maybe just a book sitting on a high shelf. Our mission today is to unpack these ideas using the physics sources you sent us.
Indeed, we'll explore how objects have energy, not just when they're, visibly doing something, but also just by being in a certain position or state.
Hopefully we can make those physics concepts click. Understanding energy, it really does change how you see things. Okay, let's get into it. Let's start with kinetic energy. This one feels, well, pretty intuitive, right? The sources call it the energy associated with an object in motion.
Exactly. If it's moving, it has kinetic energy. Simple as that.
Faster it goes, more energy, heavier it is, more energy.
Precisely. The formula they give is half mel v squared. So m is the mass, v is the speed.
And it's a scalar, right? Just a magnitude, no direction needed. And the unit is joules.
Correct. Tools for all energy and work too, which we'll get to.
Okay, so using that formula, let's say we have a heavy bowling ball, like 7 kilograms, rolling along, and then maybe a light volleyball. Both moving at the exact same speed, maybe 3 meters per second. How different is their kinetic energy?
Oh, vastly different. That's a great way to see the hem part in action.
So the mass really counts.
It really does. The bowling ball, same speed, but way more mass. It packs a lot more kinetic energy. Think about stopping them, much harder to stop the bowling ball.
Right.
It shows how both mass and speed play a role.
Yeah.
But here's a really interesting part. The speed, it's squared in that equation, v squared.
So speed has a bigger impact than mass does, proportionally speaking.
A much bigger impact. Doubling the mass doubles the kinetic energy. But doubling the speed, that quadruples it because of the square.
Wow, okay, 4 times the energy just by going twice as fast.
Exactly. Think about cars. A car at 60 mph has 4 times the kinetic energy of the same car at 30 mph. Not double, 4 times.
That definitely puts speed limits and braking distances into perspective.
Huge implications for safety, yeah. The v squared is critical.
Okay, that's kinetic energy. Energy of motion depends heavily on mass and especially speed squared. Now, how does this connect to work? In the physics sense, I mean.
The work kinetic energy theorem. It's a really powerful link.
The source is stated as net work done on an object equals the change in its kinetic energy. 1 equals delta KE.
Yep. Basically, if you do work on something, apply a force over a distance, you change its kinetic energy.
So push something forward, speed it up.
Positive work, its kinetic energy increases.
And if you apply brakes, working against the motion.
That's negative work. The force opposes the motion, slows it down, so its kinetic energy decreases. It's a direct relationship.
The example they used was a hammer hitting a nail. That makes sense.
Perfect example.
The moving hammer has kinetic energy.
Oh.
It strikes the nail, does work on the nail, pushing it into the wood.
Right. And in doing that work, the hammer transfers some of its kinetic energy to the nail. It uses its energy of motion to perform the task.
So kinetic energy is kind of like the work an object can do as it slows down.
That's a great way to put it. It's the energy stored in its motion, ready to be used, ready to do work. A wrecking ball hitting a wall is another, maybe more dramatic example.
Okay. And that theorem, 1 net irrigate, lets us calculate exactly how work changes that motion energy.
Precisely. It connects forces in motion to energy changes. Super fundamental.
All right, so that's motion covered. Let's shift gears. What about energy that isn't about moving? Potential energy.
Yes, potential energy. This is different. It's defined as energy associated with an object due to the position of the object. Stored energy.
Stored. Okay, so it's not actively doing anything, but it could.
Exactly. It has the potential to do work or be converted into kinetic energy.
Yeah.
The sources give examples like a boulder balanced on a cliff edge.
Right. It's not moving, but it definitely could.
Or an arrow pulled back in a bow. It's stationary but loaded with potential.
So it's about its situation, its position relative to other things, or maybe its internal state, like being stretched.
Precisely. It's energy of configuration or position. It's about being ready.
Okay. And I gather there are different kinds of potential energy.
Yes, the sources focus on 2 main types, gravitational and elastic.
Let's start with gravitational potential energy. PEG, I think.
That's the energy an object has because of its height in a gravitational field, like near Earth.
Like that book on a high shelf. Or the classic example, an egg on a table.
Right. The egg isn't moving, 0 kinetic energy. But if it falls,
It speeds up, gains kinetic energy. Where does that come from?
From the gravitational potential energy it had while sitting on the table. That stored energy gets converted into motion energy as it falls.
And the formula for that is PEG, M-I-H-E, mass times gravity times height.
Correct. M is mass, G is the acceleration due to gravity, about 9.8 meters or near Earth's surface, and H is the height, again measured in joules.
So it depends on mass, how strong gravity is, and how high up the object is.
Yep. And notice it depends on its position, H, within the gravitational field, not just properties of the object itself.
Okay, and here's something from the sources I found really interesting. That the 0 level for height is arbitrary. You can pick where H's 0.
Yes, that's a key concept. It trips people up sometimes.
So if I drop something from, say, the second floor to the first floor, I could measure the height H from the ground floor. Or I could just measure it from the first floor.
You could. You choose the 0 reference point that makes the problem easiest to analyze. What really matters in physics problems is the change in potential energy, not the absolute value at one point.
Ah, so the difference in height is the crucial part for energy conversion. That makes sense.
Right.
Okay, that's gravity. What was the other type? Elastic.
Elastic potential energy, P-elastic. This is energy stored in objects that are deformed, stretched, or compressed.
Like stretching a rubber band or compressing a spring.
Exactly.
Yeah.
Or pulling back a guitar string like you mentioned earlier, or the stretched strings of a tennis racket right before you hit the ball.
They're not moving yet, but they're storing energy because they've been deformed from their normal shape.
Right. The sources talk about a spring's relaxed length, its natural shape, when no forces are on it.
That's the baseline.
That's the baseline. Elastic potential energy is stored when you stretch or compress it away from that relaxed length.
And there's a formula for this too, isn't there?
There is P-elastic Nagier half kxo.
Okay, break that down. K and X.
X is the distance you've stretched or compressed it from the relaxed length, and K is the spring constant.
Spring constant. What does that tell us?
It's a measure of stiffness, how hard it is to stretch or compress the spring. It's measured in newtons per meter, and
So a really stiff spring, like maybe in a car suspension, would have a high K.
a very high K, yes. A slinky, on the other hand, would have a very low K, easy to stretch.
Got it. So elastic potential energy depends on how stiff the object is.
Yeah.
And how much you deform it, squared.
Exactly. Lots of stored energy if it's stiff and you stretch it a lot.
Okay, wow. We've covered quite a bit. Kinetic energy of motion, half mv with speed squared being super important.
Right.
The work kinetic energy theorem, Wynett theory, linking work done to changes in motion energy. Then potential energy, stored energy due to position or configuration. We looked at gravitational, PEG equals MLEO, where height matters and the 0 point is flexible.
Yep.
And elastic potential energy, P-elastic, a half kxor, is stored in deformed objects depending on stiffness and how much they're stretched or squashed.
A good summary. It sets us up nicely to think about how these energy forms transform into one another, which is really where physics gets fascinating.
Which brings us to that final thought.
Right. Think about that stretched rubber band again. You store elastic potential energy, you let go.
It flies across the room, gains kinetic energy, half mvor.
So elastic potential converts to kinetic. But is that the whole story? Where else might that initial stored energy go? What other transformations are happening, even tiny ones, as it flies and eventually stops? Something to think about as you look at the world. Energy is always conserving, just changing forms.